Today, you're going to be watching a video on sampling techniques and descriptions. We are shifting into a new unit. It is dealing with statistics, and this lesson for this week is actually going to be pretty simple. It really is going to be more so on learning how to describe and display univariate data. It is like the foundations, going over vocabulary and simple ways to display data. Okay, we're going to continue to display more data the further along we get in this unit. So this is just basically the introduction. Okay, so lots of vocabulary. So we're going to start off. Okay, a census is the most accurate way to investigate a population of interest. Okay, I'm just going to do a shameless plug here. The whole census of 2020, that is the government's way of basically trying to figure out exactly how big, how many people we have here in the United States. However, in most situations, it is impractical and impossible to obtain data from the entire population. As you probably know somebody who has not filled out their census yet, and I believe the deadline is this week or has already passed, and so it is pretty impractical. I mean, but they do it so that they can get an idea. Okay, instead, a better way for them to get information probably would be to conduct a survey of a well chosen sample of the population. But when you think about the U.S., what really is a well chosen sample? So, but we'll talk about a sample right now. A sample is a smaller group chosen from the population. Okay, so maybe instead of the government trying to collect data from every single human, maybe they can just collect it from like certain people from each of the states. Okay, that would be a sample, and a random sample is one where each element has the same chance of being included. A bias sample is one that's not random. So if they wanted to do a sample instead of an entire census, maybe they would just collect people just randomly, like they just got a phone book of everybody in that particular state and just picked out randomly, just opened it up. But a bias sample would be like if they only chose people from Los Angeles, New Orleans, New York City, Miami, like major cities. That would be an example of a bias sample, not a random one. Okay, now when we collect data, we collect it to estimate a characteristic of the population. Our estimate will most certainly be different from the actual characteristic of the population, and that difference is referred to as an error. Error. Sorry, this is going to be my hard word for this lesson. So, four categories of error. There's four different types. You have a sampling error, a coverage error, a non-response error, and a measurement error. Now, a sampling error occurs when a characteristic of a sample differs from that of the whole population. This error is random and will occur even for samples which are well chosen to avoid bias. Now, coverage errors occur when a sample does not truly reflect the population we are trying to find out about. Okay, the easiest way to avoid a coverage error is the sample should be sufficiently large and unbiased. So let's say you wanted to collect information regarding Lake High School. You want to try to get as big of a sample as possible, maybe not just the people in your class. Um, another thing, another example, let's say you're interested in marine wildlife and you're trying to determine the health of all the dolphins that you have or something like that. If you only get data from like one particular like pool of water that you have some of your dolphins in and not all the pools, okay, then that might not be representative of all the dolphins that you have, right? And so, that would be a very much a biased sample, and it wouldn't cover the entirety of what you actually have. A non-response error is one that occurs when a large number of people selected for a survey choose not to respond to it. It's I mean, you see anytime that administration sends out a survey, okay? You always have those students that are like, I'm not going to respond to that survey, especially if it's online. Things get lost in email. Some people might even get the email. And so the people who don't respond, that would be a non-response error. Okay. And the last error is a measurement error, and that refers to the inaccuracies in measurement at the data collecting stages. So, for example, let's say you went around and you got data of people's heights to the nearest centimeter, and you recorded the height as slightly different from the person's exact height. let's just say you mismeasured them, let's say because you took a measuring tape yourself, or they estimated how tall they really were. That would be an example of measurement error. Okay, now those are some things you have to kind of take into consideration when you are dealing with statistics and data or data. The next thing we're going to be talking about is your sampling techniques. So when you go out to pick up data, there are 5 different sampling techniques that you could use. You have simple random sampling, systematic sampling, convenient sampling, stratified sampling, and quota sampling. If you notice, stratified and quota are like linked together because they are similar. Okay, but we'll talk about each one of those in its own. Okay, so a simple random sample is let's say that 3 students are sampled from our class. The names of all the students were placed in a hat, and 3 students were names were drawn from that hat. Okay, if you notice, every student would have this same chance of being selected, so that would be 1 out of, how many we got in our class? 9. 1 out of 9. Okay, and each set of 3 students is just as likely to be selected as any other. Okay, so it could be selected as Lydia, Logan, and Alex. They're just as likely to get selected as Zach, Alicia, and Callie. Okay, um, that's an example of simple random sampling. Okay. Now, systematic sampling is when you are selecting your sample, or you're getting your sample by selecting at random intervals. Okay, let's say you stand at the door of morning meeting. You know, if we still have morning meeting, let's say you stand at the door of morning meeting and you were collecting the grades of every 7th person that came through your particular door. Okay, that would be an example of systematic sampling because you're collecting every 7th person. So you get that first person, you count 1, 2, 3, 4, 5, 6. There's the next person, you get their grade level. That's an example of systematic sampling. Convenient sampling. Convenient sampling, in many situations, people are chosen simply because they're just easier um, to get to, or they're more likely to respond. Okay, let's say like you guys were, let's say I assigned you guys a statistics project or something like that, and I asked you to collect some data. A convenient sample would be you guys just selecting each other because you guys are in the same class, you guys are doing the same project, you know the weight of that project, and so the people in your class are more likely to respond. But if you were to try to go to like Miss Childress's class, or like a kid that went to another school, um, that wouldn't be a convenient sampling because they probably are not as likely to respond because they're like, what does this project have to do with me? You get what I'm saying? They're close in proximity to them, um, and they're more likely to respond. The last 2, stratified and quota sampling, they're useful when a population can be divided into subgroups, and each group is represented fairly. For example, let's say Mr. Saran wanted to collect opinion from the students about how digital learning is going, right? To make sure that each grade level is represented fairly, then the number of students that are sampled from each year should be proportional to the fraction of the total number of students in each grade level. So I don't know how many students are in the junior class, but they will want to make sure that that proportion is a good representation of how many juniors actually represent Lake Wales High School. You don't want to have 100 juniors respond and only 2 freshmen. That's not an accurate representation of the population at Lake Wales High School. Does that make sense? So that's what stratified and quota sampling is. It takes a group, divides it up in subsections, and makes sure that every group is represented fairly. Stratified, though, is when you do it randomly, and quota is when you do it biasly. So bias would be you only get data from IB students, okay, because they're the ones who had the Chromebooks from the beginning, right? Not like every other student from Lake Wales High School. Stratified is more random. Whoever responds responds. okay? But even still, that could be pretty biased because some people are still without a device. But that's neither here nor there. That's for another day. But those are your different sampling techniques, okay? So you have your different types of error, your different type of sampling techniques, and now we're going to actually be talking about our univariate analysis. Okay, univariate involves a single variable, such as heights in a class. Okay, now there are two different types of univariate data. You have your qualitative data, which is also known as categorical. Those are things that can be divided into categories, such as what's your favorite type of candy, or who's your favorite artist. That's an example of categorical. The responses are things that you can divide into different categories. Quantitative is data that can be counted or measured, such as number of CDs you have and the length of time it takes you to finish a race. Within quantitative data, you have two different types of data. You have discrete and continuous. Discrete is things that can be counted, whereas continuous is things that can be measured. And I know some of you guys are gonna like when we come to determining what's discrete versus what's continuous, we might have a few discussions about the why is this continuous or why is this not continuous. But just remember, if you have to measure it, like literally have to like I don't know how to like measure it, it's going to be continuous. Discrete has a definite number that you can sit there. If you want to, you can count every single one of those CDs or every single one of those people that are in that room. Okay. Now, when you're doing a statistical investigation, like I said before, the whole group is known as a population. All right. Some other examples of discrete and continuous data before I actually keep going. Discrete would be like the number of limes on a tree or the number of players that play a game. Continuous would be like the distance a baseball players hit a ball, or um, oh wow, I'm drawing like a major blank now, or the average temperatures in various cities. Okay, those are examples of continuous data. All right. Now, when you have a large amount of data, it sometimes is easier to interpret the data if it's organized into a frequency table or displayed as a graph. What you see there, that's an example of some data that has been arranged into a tally table, a tally column, a frequency column, and a relative frequency column. Now, the tallies really aren't necessary, but let's just say you have like a whole bunch of data. You could recognize what each of like the X values are, and you just have to go through and count them. A tally column is just a easy way to kind of keep track of all the numbers that you have. You're more so likely to have a frequency column besides your X value column than a tally one. So you're more likely to have value and frequency because the frequency is nothing but counting up the tallies. Okay. Now, your relative frequency of a data value is the frequency divided by the total number of recorded values. This indicates the proportion of results that take that value. Very rare that you'll deal with the relative frequency, but it is a way that you can represent your data. Okay. Once you get all your data in your frequency table, it can be displayed as a column graph, aka a bar graph. Okay. For this type of graph, the possible data values are placed on the horizontal axis. As you guys see, the X values were 1, 2, 3, 4, and 5, so they're placed there. The frequency is what's placed on your vertical axis. The column width are equal, and the column heights are represented by the frequency from the table. And there are gaps in between. Gaps are always in between your columns because your data is discrete. One thing I want to make sure that I always point out is that if you ever have to draw the graph yourself, you always make sure you label your X and Y axes. Just to review real quick, the mode of your data, you guys remember that word mode? Remember, mode represented the most, okay? The X value that had the most data. In this case, the mode would be 2. Very good. The tallest bar. Right? Now, when we describe the distribution of a data set, okay, when we describe how your data is displayed, how much is spread out, you can use the column graph to kind of look at the shape of it, okay, and we can either describe it as being symmetric, negatively skewed, or positively skewed. Symmetric would be that it is is equal about the mode. Okay, so pretty much it's kind of even on both sides, nice and centered. Negatively skewed is that the negative side is more stretched out. You have like smaller, 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 bigger, bigger, and then small again. Positively skewed is the reverse. So if you were to look at this last example, if I wanted to kind of like trace over this just a little bit, you would see that this one, and mind you, I'm doing this with just my trackpad on my laptop. This would be an example of positively skewed because the positives are a little bit more stretched out. All right. You can't forget about outliers. Okay, outliers are data values that are either much larger or much smaller than the general body of the data. If it is a genuine piece, then it should be retained for any type of analysis, mean, standard deviation, etc., etc. But if the result is an error, it should be removed. Okay, so you want to make sure that you're aware of that as you're doing these different types of problems. Now for um, grouped discrete data, as you can see, I have an example here. This just represents the number of vehicles that are passing by between a particular time frame. This is a lot of data, and to be honest, there's not much repetition of certain numbers, and so just a regular frequency table would not be beneficial here. So you would want to do a group frequency table. That's when you condense. You kind of break the data off into what's known as classes or groups, and then compare the frequencies of the classes. Okay, for this data, yes, you can see the width was 10. The width is determined by seeing, okay, from this to this, this to this, this to this, so on and so forth. That's how large each of the classes are. And if you notice, all of the class widths are equal. One is not bigger than the other. So if you do a a grouped frequency table, you want to make sure that your intervals are of equal width. The modal class would be the class that has the largest frequency, so that would be from 20 to 29. And we can also see it even from the bar graph off to the side. Again, the x-axis and the y-axis are labeled. X-axis with your x values, which represent the number of cars, your y-axis with the frequency of the cars themselves. And continuous data. To wrap this up, continuous data, the other two examples were for discrete data like number of CDs and et cetera, et cetera. Continuous data, though, is for just realized I spelled that wrong. Continuous data is for like your distances and your temperatures and things like that. This is data that can be grouped into class intervals of equal width as well. But this is where we don't know, like, this continuous data can also be for values that we don't know the exact value for. Okay, we may know an approximation, which is why we would use a different type of graph than the graph that we use for discrete data. Um, this does come from a frequency table with classes that are of equal width. The only difference is that instead of doing a bar graph, you would do a histogram, okay, or a frequency histogram. It is what you use when you're doing continuous data. So a bar graph is for discrete data, a histogram is for continuous data. As you can see, there are no gaps in between your bars. That's what makes that graph that you see a histogram instead of a bar graph. Of course, the x and y axis are labeled, which is always wonderful. And again, so the modal class will be the class with the largest frequency. So in this case, even though we don't have a frequency table, just based off of our observation, we can see that the modal class would actually be from 8 to 9 because that is the largest bar there. We can also see that the whatever this was based off of, which was probably scores in a game or something like that. The smaller score was 4, and the larger score was roughly 12, approximately. Okay, we can see that there were maybe 4 games that had a score that was between 4 and 5. There were 5 games that were between 10 and 11, and so on and so forth. So we can make conclusions from the graph even though we don't have a frequency table. And this is the start of statistics. You have your basic definitions of the different types of area you have, the sampling techniques, the different types of data. And that's what this week is really going to be more so just practicing that terminology to make sure you guys got it before we go kind of full head on in into the different types of statistical applications that you'll be dealing with. So, if you have any questions, please make sure you pop onto my lives and yeah, let me know.